So with today's lecture, we're going to take the concepts that we learned in solution chemistry and in equilibrium and apply them more specifically to solutions that are acids and bases. So to do that, we're going to identify essentially what an acid and base is. What are the different definitions? There's multiple definitions. We're going to focus on two. And then we're going to give examples of where we can find acids and bases. And we're also going to name some of the acids and bases to help us identify which ones are strong and weak and what is the difference in their characteristics. So there are several definitions for acids and bases. And we've slowly been exploring these definitions. We did when we went in chapter 6 with chemical reactions, and we were discussing double displacement reactions, one of the double displacements being neutralizations. So what definition you use really depends on what you're studying. Okay, so one definition we won't discuss is Lewis acid and base, because that's really popular in organic chemistry where there's not a lot of water, but we're focusing on water. So we deal with equilibriums and solutions in water. So our definitions are going to be slightly different than that. So we'll cover the most common ones. So an acid is a substance that essentially produces protons. So we've discussed this in the past. The hydrogen ion essentially is a proton. The reason why it's a proton is the hydrogen atom has a proton in its nucleus and one electron. If you lose an electron, all that's left in the hydrogen is a proton. So a lot of times, the hydrogen ion is referred to as a proton. So an acid is anything that releases a proton in water. A base is anything that will basically dissociate and produce a hydroxide ion. So this is how a base can be defined, something that produces a hydroxide ion. We saw this when we did the neutralization reactions, the double displacement, where I wrote, you can generically write out the acid as HA and the base as BOH. And then in the double displacement, right, we're switching partners. We're doing kind of a do-si-do here. And we end up getting water, which I had you write as HOH to help you balance it, and the salt. So we've seen this definition, and this is your Arrhenius definition. This is the most common, the simplest of all definitions, is looking at something and just saying, oh, there's a hydrogen that can be produced in water, it's an acid. There's a hydroxide, it's a base. It is by far the simplest, and it's the one that we've already seen. So again, these are restricted to water solutions, and that's okay because that's what we're primarily dealing with. So an example of an Arrhenius acid is, I could take hydrochloric or hydrogen chloride gas, throw it in water, and it dissociates 100%. So it'll break apart to give me these protons and a chloride ion, and it will be 100% dissociation. So it will completely break apart, giving me if I have 1 mole of hydrogen chloride gas, it'll give me 1 mole of protons and 1 mole of chloride ions. So one of the things you want to realize are acids are actually electrolytes, because electrolytes are essentially a solution that has ions, and the ions allow for conductance of electricity in solution. The other thing that you want to know about acids is they have a sour taste, right? So citric acid is an example of an acid found in citrus. If you had litmus paper, they would turn the litmus red. They also neutralize bases. So these are things, turning litmus, we've worked with litmus paper, we've done neutralization reactions, and we've talked about the dissociation of acids and electrolytes. So here are 2 examples. we have nitric acid, and they actually draw the Lewis dot structure for you, which is really nice. And if you look at the nitric acid, what they're omitting is the lone pairs. So really this would have your lone pairs there, and your lone pairs, so that everything has an octet. But this is nitric acid. It is essentially a nitrate that has an extra hydrogen attached to it. This is my acetic acid, right? So my lone pairs would be there, my lone pairs would be there. So these are two examples of acids. And what makes them acidic is that right here in this bond, there's two electrons. And when I throw this in water, the oxygen steals the hydrogen's electron, and I end up getting an H plus ion, and then the nitrate group is left over. And the electron that the nitrate stole would be right there. And that's where the extra, negative charge from NO3 minus comes from. So nitrate, right, is derived from nitric acid. Once it steals that hydrogen's electron and releases a hydrogen ion in solution, it's behaving as an acid. So with acetic acid, it doesn't do it as well. And that's where we actually get, instead of one-sided arrow. So when you have nitric acid and you throw it in water, you'll see a one-sided arrow. And the reason why you see a one-sided arrow is this is a strong acid. And it dissociates 100%. If you throw acetic acid, it's a weak acid. So what you see is the double arrow because it's in a state of equilibrium. And it will produce, and this is why they write it as CH3COO minus sometimes, it'll produce the acetate ion, which we've written out in the past as CTH3O2 minus, and a proton. And that electron that I circled right there is the one, it's actually in this bond, that the oxygen stole from that hydrogen. So bases are a lot easier. I love bases. Why? Because typically they're going to end in a hydroxide. So when we think of Arrhenius bases, right, they produce a bunch of OH minus hydroxide ions. So if I add sodium hydroxide as a solid and I throw it in water, right, so that's what they're showing right here. It's an ionic compound. We know group 1, right, group 1A alkali metals are always soluble. It dissociates into my sodium ion and gives me a bunch of hydroxide. So that's how we measure a base, by the hydroxides. They're a lot easier, right? Now, they're bitter. They're also electrolytes, because electrolytes just means they produce ions in solution, and they do. They feel, so your soaps typically are basic, and they give you that slippery, soapy feel. So they're typically they're basically conjugate bases to really weak, long chain carboxylic acids. That's what soaps are. They're carboxylate ions. And the other thing is we saw that bases neutralize acid in the earlier discussion of neutralization reactions.